In this video, we look at how to describe the rotation of a diatomic molecule. Let's start with the simplest possible model for a diatomic molecule, a two-body system with two masses, m1 and m2, separated by a fixed distance, r. If unconstrained in space, this molecule can rotate. The rotation is around some axis of rotation that passes through the molecule's center of mass. Let's assume here that the molecule is rigid, so the bond does not vibrate. We're also going to neglect any centrifugal forces acting on the two masses due to rotation. Like in the case of the harmonic oscillator, this two-body situation can be transformed into an equivalent one-body situation that is mathematically simpler to treat. This transformation yields a single body of mass mu rotating around the center at a fixed distance r. Mu is the reduced mass. And it is equal to m1 times n2 divided by m1 plus m2, just like in the case of the harmonic oscillator. The mass rotates with a certain rotation frequency. Which we indicate by nu rod. The actual velocity of the mass, v, is the product of this frequency nu rod times the path traveled, which is the circumference of the circle, 2 pi r. We can group the 2 pi with the rotational frequency and write this as omega rod r. Omega rod is the rotational angular frequency, or the angular frequency of the rotation, omega rod, often just simply denoted by omega. Now, the kinetic energy of the mass is the following. T equals p squared over 2 mu, where p is the linear momentum, or alternatively 1/2 mu v squared, where v is the velocity. Now if we insert the expression from above, we get 1/2 mu omega squared r squared. Now if we collect the constants mu and r, this becomes 1/2 mu r squared times omega squared. This product, mu r squared, is called the moment of inertia. And denoted by uppercase I. I equals mu r squared. With this, we can write the kinetic energy as 1/2 I omega squared. We can also define the angular momentum. Uppercase L, which is equal to mu times the velocity times r, which is equal to mu times r squared omega, which can be written as I times omega. With the angular momentum, the kinetic energy can also be written as T equals L squared divided by 2I. If you compare this expression with the very first one for the kinetic energy, you see that L, the angular momentum, is equivalent to the linear momentum p, and I, the moment of inertia, is equivalent to the reduced mass mu. This equivalence is worth spelling out in a table. linear motion on the left, and rotational motion on the right. The mass for linear motion, m, is equal to I in rotational motion, which is the moment of inertia. And the linear momentum, p, for linear motion is equivalent to the angular momentum, L, for rotational motion. So you can use your intuition you have developed for linear motion and transfer it in a fairly straightforward manner to rotational motion. Just keep in mind the equivalences listed in this table. In summary, we have reduced the rotation of a rigid diatomic molecule to the rotation of a single mass at a fixed distance from a center. The most important quantities for describing a rotational motion are the moment of inertia and the angular momentum. These two can be used to express the rotational kinetic energy as L squared over 2I.